All right, everybody, so this is the next part of our review for your study guide. So we're going to go through section 2.6, so unit 2, skill number 6, and we're going to talk about the rate of dissolving. So let's go ahead and fill in these blanks that kind of explain what's going on. So it says not all solutes will dissolve at the same rate, which means speed. Okay, so they won't all dissolve at the same speed. The rate or speed that the solute will dissolve depends on if it is a solid or a gas and the various factors. So in order to increase the rate of a solid or how quickly it will dissolve, you need to increase the number of collisions between the molecules. In order for sugar to dissolve in water, the molecules have to collide. And there are 3 external factors that affect the rate of a solid. The first one is the temperature. The second one is whether or not there's any stirring or agitation, like shaking it or anything like that. And the third one is surface area. And there are only 2 factors that affect the rate of a gas. One of them is temperature, just like solids. And the second one is pressure. Now, remember that temperature measures your average kinetic energy, which means the speed of the particles. Remember, kinetic means movement, so it's telling you how quickly or slowly the particles are moving. So in order to increase those number of collisions, solids will need a high temperature because that means they're moving quickly. But gases will need a low temperature because they want to move slowly so that the gas, imagine a soda, you want the gas to stay dissolved and not have enough energy to escape your soda. That's when your soda goes flat. Now, the thing about surface area, because stirring is pretty self-explanatory, but surface area is sometimes tricky. So one thing to keep in mind is that the higher the surface area you have, the smaller the pieces are, which means a solid needs a high surface area to dissolve quickly because it will increase the number of collisions because there is more particles. So keep in mind, if you have small pieces like a powder or something like that, that means that you have a high surface area. If you have really large pieces, then that means you have a low surface area. And solids want a high surface area, so small pieces. So when we look at question 1, it says, at which temperature will a solid dissolve the fastest? 50 degrees Celsius or 80 degrees Celsius? What about a gas? Explain why. So when we talk about a solid, okay, a solid, we know from what we just read and wrote down is that a solid will need a high temperature to dissolve quickly. So when we want to know the fastest, we need a high temperature. So a solid will dissolve the fastest at 80 degrees Celsius. Now, when we want to explain why, we need to think about what temperature is. Temperature measures our average kinetic energy or speed. And we know to increase the number of collisions, that's how we increase the rate or make it go faster. So in every explanation about rate, you should be talking about collisions. So we can say that having a high temperature, okay, which I'm just going to abbreviate temperature, a high temperature means faster particles and more collisions. So it will dissolve faster. Okay, any good explanation of rate for a solid or a gas will include how it changes the molecules and how it changes the collisions. What happens to the collisions to change the rate? And there was a second part. It wanted to know about a gas. Well, remember, a gas needs a low temperature. Okay, it does the opposite with it. So a gas will dissolve the fastest, not at 80 degrees, but at 50 degrees, because a lower temperature means, so a low temp means slower particles, and the molecules collide less often. Now, I could have worded it exactly the same way as I did as a solid, just in opposite, but I wanted to show you a couple different ways that you could word your sentences. Remember, they don't have to be exactly like how I wrote it, but you want to have the same ideas. You're talking about the collisions, if you're talking about temperature, you're talking about the speed, and you're actually giving an answer, okay? If we look at question 2, it says which solid, okay, so this is important, it's a solid, so we're going to think about a solid, will dissolve the slowest according to the data table. Now, when I have this kind of data table, and we've got 2 experiments, we've got experiment A, oops, that's huge. We've got experiment A and we have experiment B. So what I do is I look at each thing. Now, if we're looking at a solid, for a temperature, these are the same, which means you can ignore them. Temperature will not change. If the temperature is not changing, then it's not going to be what determines if something's going to be slow or fast. Now, stirring. We know that if you stir, that makes a solid dissolve fast, and not stirring makes it dissolve slow, right? If you're trying to dissolve sugar in your Kool-Aid, you stir the sugar in your Kool-Aid. You don't just sit there and stare at it. You know it helps it dissolve faster. And then with surface area, here's the thing. Because it says large, that makes it fast, and small is going to be slow. But remember, that's because it said surface area. If it had said particle size, okay, then something with a large surface area has small pieces, and something with a small surface area has large pieces. So you have to pay attention to how it's labeled and what they're talking about. So now that we've labeled these though, we can compare it to what the question asked. It said, which one will dissolve the slowest? Well, we can see that experiment B has 2 things that make it slow, whereas experiment A makes things fast. So we can say that experiment B will dissolve the slowest because it does not have stirring. Oops. Does not have stirring. And there is a small surface area. Now, this is an excellent answer, but I did not include information about the collisions in this sentence. So in order to get full credit, I need to write one more sentence that says this will decrease the collisions and slow it down. Okay, so that is the key part, is being able to talk about the collisions and getting experiment B is the slowest, and talking about the stirring and surface area. Those are the key features of an answer that's going to get you full credit. Now, if we look at question 3, it says, which gas will dissolve the fastest according to the data table below? So again, we're going to do the same thing. We're just going to look at what it is. Now, this is a gas. So when we look at temperature, remember, for a gas, fast, for a gas, fast dissolving means a low temperature. So 10 is lower than 25. So we're going to label these fast, fast, and slower. Faster, slower. Okay. And if we look at pressure, okay, for gases, if you want to move fast, you need to have a high pressure. So that would make these faster, faster, and slower. And the reason why this is helpful to label it that way is when we then look here, we want to know which one will be the fastest. Well, experiment B is the only one that has a pressure and temperature that is faster than the other ones. So we can put an explanation there. So experiment B will dissolve the fastest because it has a low temperature and high pressure this slows the molecules, right? A low temperature slows down the molecules, and the pressure keeps, like almost pushes, we can just say pushes the molecules into the solution. Like it stays dissolved because it's basically like pushing it into the liquid, like making it stay. Okay, this is why you know that you can have a can of Coke, and as long as you don't open the Coke, like as long as you don't pop the can and hear the psh, then it will stay bubbly forever. But as soon as you open it, the pressure goes down and the gas will start to escape. Okay, so that was rate of dissolving. And again, it's very dependent on talking about which one is correct, why, and how it affects the molecules and collisions. So if we look at section 2.7, okay, this is the last section in Unit 2. It says, when compounds dissolve, there are two possible processes, solvation and dissociation. Now, solvation is when the particles separate and the water surrounds them. Okay, so anytime you have particles separating and water surrounding each of those particles, that is solvation. And this happens when when all compounds dissolve. So every time you have something dissolve, solvation happens. And this means it's both ionic and covalent compounds, so both of them. Now, dissociation is when an ionic compound separates into the cation, which remember, cats have paws, so cations are positive, and the anion, which is negative. Okay, and so because water is polar, meaning it doesn't share its electrons equally, the oxygen kind of pulls the electrons more, it's a bully. Okay, the hydrogens will have a partial positive charge, and oxygen will have a partial negative charge. So when we draw a water molecule, there are two kind of ways you might see it. You might see it like this is called the stick and ball model because it's like the metal or the elements and you've got those two. So we would say that oxygen has kind of a partial negative, whereas hydrogens are partial positive. You could also draw it like if you have like the model like this, where you've got your oxygen and your two hydrogens, you might draw it like negative and like little positive signs in there. And the cation is surrounded by water, but because the cation is positive, the water rotates it so that the oxygen atom is near it, while the anion is surrounded by water that is rotated so the hydrogen atoms are near it. So the way this looks is, let's say I have my cation. Let's not use purple. Let's use gold. So if this is my cation and it has a positive charge, your water is going to surround it, but when it does that, all of your water molecules, which right now I'm just drawing the oxygens, will have the oxygens pointed to it. So the hydrogens are going to stay away because we know that opposites attract. The positive is attracted to the negative charge in this water, and so it pulls it that way. Whereas the anion, which has a negative charge, when it has the water surround it, okay, so again, the water surrounding, that's solvation, but the fact that the positive and negative are separated, and when the water surrounds it, in this case, all of the hydrogens will be pointed towards it, because the hydrogens have that partial positive, which it's almost a little too small for me to draw my plus signs there, but it's going to have opposites attract. Okay, so the surrounding is solvation. The separating of the positive and negative, that is dissociation. And so one thing you have to be able to do is decide if something is ionic or covalent. Now, if something is ionic, that means it has a metal and a nonmetal in the compound. If it's covalent, that means it has only nonmetals. So as a refresher, when you look at your periodic table, let's say this is our lovely periodic table that I just drew. You have a staircase that kind of breaks it down. And so metals are on the left side and non-metals are on the right side. However, there is a SPI. Hydrogen looks like it's a metal, but it's actually a non-metal. We call it the SPI behind enemy lines. It crossed over into metal territory, but it's actually a non-metal. It's trying to trick you. So when we look at this, we want to label them as either ionic or covalent and decide if it will undergo solvation, dissociation, or both. So, okay, sorry, my tablet scrolled. So when we look at NO2, nitrogen is a nonmetal and oxygen is a nonmetal. So this is covalent, which means it will undergo, remember, look up here, solvation happens in both of them, but dissociation only happens with ionic. So that means covalent compound will experience solvation only. If we look at B, we have magnesium, which is a metal on our periodic table, and chlorine, which is a nonmetal. So that would make this ionic, and that means it will undergo solvation and dissociation. So it will be both. So you should be able to then go through and figure out whether or not the remaining ones are ionic or covalent and model it. If it's ionic, it will experience solvation and dissociation. If it's covalent, it will experience solvation only. Now, when we look at question 2, these pictures, it says describe how each of the following pictures specifically shows either solvation, dissociation, or both. So if we look at picture 1, we see here that all of these, carbon, hydrogen, oxygen, those are all nonmetals, which means that this is covalent. Okay, now because it's covalent, that means we should see solvation only. It also means that there are no positive or negative charges. So because there are no positive or negative charges, the water is just going to be random. We're not going to see positive and negatives in the water. And so here we see that the water molecules are all surrounding the particles and they're separating. So we can say that picture number 1 shows solvation because the particles separate and the water surrounds it. Okay, now you could explain why it's not dissociation, that there's no positives and negatives and things like that, but this would be sufficient. Now, if we look at picture number 2, we see that there are anions, which are negative, and cations, which are positive. And here we see that the hydrogens are near the negative one, and the oxygens are near the positive, and that water surrounds them. Now it's showing it surrounding it slightly different than the way I showed you earlier, but this is perfectly fine. So we can say that picture number 2 shows solvation and dissociation, okay? And we can say it shows solvation because the water molecules surround the particles, and it's dissociation as well because the cation and anion separate, which is spelled with an E, separate, and the water rotates based on the charge, right? How the oxygen is near the cation and the anion has the hydrogen surrounding it. And so that is solvation and dissociation. And that's the last part of your Unit 2 review.